Hello and welcome to March 2022. I don't know how many bingo cards you've thrown out so far this year, but I think I'm on my fourth or fifth. But welcome to OWASP Ottawa March 2022 meetup. Just to introduce a few things from our public service announcement, become an OWASP member, you get lots of perks. And you get to support our community, all our events, and your chapter. We would like to see your presentation, and we're open to all kinds of different formats, from lightning talks to middle-ish kind of talks to full presentations. And if you want to do a slam poetry security session, we'd be open to hearing about that as well. You can connect to us on all these different platforms, some of which you, if you're watching this, you already know about, but we have our own Slack. Not because we like to have our own Slack, but we started there first. You can connect to us on LinkedIn as well as on Twitter. Our Slack has a jobs channel, so there are relatively frequent posts there of jobs in both the Ottawa area and in that remote world. The executive director of OWASP has his office hours. So if you wish to set up a meetup with him, you can check out this link. There is also the global OWASP Slack. This you need to be an OWASP member for, so that's one of the perks, and it is got a lot of OWASP goodness in it. Special shout out to the people that help with OWASP Ottawa, including Rick, Dave, Sharif, Adam, and Scott. As well as OWASP is busy, so there's a number of new projects out there, including new versions of projects. There's a new version of Juice Shop, Secure Code Box, and Amass, and something called Wrong Secrets, which I have to check out. But what you're all here for is our presentation. So I would like to introduce friend and serial presenter to OWASP Ottawa, Ben Gardner. Ben is an independent consultant and has been so for a number of years with Yellow Flag Security. He is a volunteer at several hacking villages, including, and I'll get the name right here if I can actually find it, the DEF CON Hardware Hacking Village and Car Hacking Village. But today he's going to talk to us about Radare2 and Jupyter notebooks. So welcome, Ben.
Hi, thanks for having me.
So I'm going to stop sharing my screen, and I will let your screen come in. Awesome.
Perfect.
Welcome. Thank you for sharing with us again. And sorry for the clogged internet pipes there, but
No worries.
We'll have to find out what's going on.
Oh well, it's all good. Thanks, Garth. Hi, everybody. I see a couple familiar faces in the YouTube chat. Thanks for saying hi. I am here today to talk to you about Radare2 and Jupyter notebooks. Going to cover quite a bit of material. If you've suffered through one of my presentations before, you'll know there'll be a lot of information density. This is the agenda. You may not know what Jupyter notebooks are, Radare2 is. I'm going to make sure you do. I'll make sure you walk away knowing what R2 pipe is, what Anger is. We're going to look at some micro-corruption challenges. We're going to look at an awesome SNES challenge by Zach at NSEC. And then something that I thought was a bug, which is not. So spoiler, it's not a real bug hunt. But we'll work through all of that. I think Garth did a great introduction for me. Thank you very much. And thank you to all the OWASP Ottawa volunteers for making this possible. So let's get into it. We started late. What is Radare2? It is a reverse engineering framework. You're going to be seeing a lot of it. There's some screenshots here of it, which I snipped from the Radare2 homepage. I like using it just as a hex editor and hex viewer. It's great at that. There's really good entropy plots and other utility functions in it. But first and foremost, it is made for reverse engineering, so disassembly is a primary function. Quickly before I forget, I am more than happy to answer questions as we go along. So I do have my eyes on the StreamYard comments pane, which is supposed to be receiving your comments from YouTube. If you have a question, go ahead, pop it in there at any time. I prefer to be interrupted and answer your questions during the presentation than lose you at any point during the material. So the other half of this presentation is Jupyter Notebooks. They are interactive environments. They can run all kinds of languages. Python is kind of the default. And they facilitate, what I like to think of as literate programming, although I think that might mean something different to other people. Here's a screenshot of their homepage. Technically, we are talking about Jupyter Labs, although I keep saying notebook, even though I'm not supposed to. I'm kind of stubborn that way. I also keep saying SSL when I should say TLS. Maybe I will never learn. You are actually looking at a Jupyter notebook, and Garth posted the link to this Jupyter notebook at a gist, so a GitHub gist that's hosting it. The rendering of Jupyter notebooks on GitHub gist is pretty cool. It will show you both the input and the output and any embedded images, which is great. This particular notebook is right on the edge of what GitHub will happily render in their back end. Pro tip, if you spam refresh enough, you will eventually get a rendering of it. There seems to be something with the renderers. Some of them are a little more forgiving with the size of the notebook than others. So you will eventually get a rendering if you spam F5. But by far the best way to interact, if you want to follow along and not just look at my screen share, is to install Jupyter Labs on a Linux box, because this will be spawning out to Radare2, and see if you can follow along. You probably have to run a couple pip install commands during. And once again, if you need any help, go ahead and shout out on the comments section. Oh, I'm glad that Pocket Java also keeps saying SSL. I don't feel so alone. So why would I do this? Why would I bother shoving Radare2 into Jupyter notebooks? Do I love doing strange things? Yes, I do. But also it does kind of fulfill a need that I feel like I've had in the past with Radare2. So Radare2 has this feature called R2 pipe. And R2 pipe is this, oh, you can see I just executed my notebook right there. R2 pipe is this great programming language binding for Radare, and the language compatibilities that are available are numerous. There's Go, there's Python, there's JavaScript, etc. The one we're going to use, because we're in Jupyter Notebooks, is obviously Python. There's kind of a key feature to it. Radare2 has all of these JSON outputs where you can throw the letter J on the end of a command and it'll emit JSON, and R2 pipe has these command variants where you can throw a J on the end of command and it'll automatically parse all the JSON. So you get like a language native structure on the other side. So here in Python, you get a dict, and that can enable all kinds of automatic scripting of powerful stuff that Radare can do. Because one of the things that Radare can't really do is control flow of the scripts. You can easily iterate over things, but you can't necessarily do conditional execution very easily in Radare. So popping out into scripting languages like Python with R2 pipe is very powerful. So using R2 pipe is pretty straightforward. Why don't we look at an example here? We're going to obviously import R2 pipe. We're going to open up dash, which is common term for standard in. So open up nothing. We're going to tell Radare to go ahead and do no analysis. So don't bother looking for file headers. Just open it up. Then we'll tell Radare cache IO writes, so it'll make a memory map section that'll do a copy on write dirty, and then we're going to write some hexadecimal, and then we're going to disassemble 4 instructions of it. So we hit Shift Enter here on my keyboard, and it executes all of that. And you can see it printed the output of this Radare pipe, this Radare command PD4 through R2 pipe via the command method on the R2 pipe object. And we get this nice disassembly, which is great. And we're looking here at a location finding gadget that you might have seen if you're working on some shellcode. We put this one together at Ron Bow's workshop at Montrehack a couple weeks ago, which was a lot of fun. Where this falls short for me in the kind of workflows that I get into, particularly when I'm trying to make sense of things with some reverse engineering, is colors. I really like to look at colors. It makes a big difference for me. So enter this really simple wrapper. It forces the color output of Radare to true and picks, absolutely unequivocally the best color scheme. No apologies. And then it does some nice things like splits the lines and does each command for me one at a time. So what you saw above, the exact same thing can be done with this multi-line string block, which I find a little bit easier to work with when I'm doing larger commands. And the result, well, of course, I have to execute the definition of the function first. The result is pretty colors, which may seem silly, probably is, but does make a big difference to me. So there you go. But behind the scenes, we're still using R2 pipe. Now, if the whole talk was really just me showing you this one silly trick, you would be done now, and you would probably be disappointed. What we're going to do is take this one silly trick, and we're going to apply it to a couple different things. So the first thing we want to apply it to is some microcorruption challenges. So what is microcorruption? This is a really amazing online CTF, like an asynchronous CTF that you can do at your own pace. It introduces you to embedded security. It introduces you reversing of embedded systems, particularly things that don't have a lot of symbols in later levels, and also how to exploit those systems. It was made originally by Matisano Security, which was acquired by NCC Group, and NCC Group keeps running the challenge like absolute legends. So many, many thanks to them. You can access it at microcorruption.com. Here's a screenshot of what you might see. And then, of course, you have to sign up and get an account. And the challenges are going to look like this. You have access to a disassembly area. There's a live memory dump, which when you start the level is just the initial contents, which definitely covers the disassembly, but has more data in it than what you would see in the disassembly. So you need both of these things to get the full challenge. And then there's nice debugger stuff. So it'll show you current instructions and your register state. This is all based on the MSP 430, which you may be familiar with. And if you aren't, then by doing microcorruption, you certainly will be. So you can actually debug it here and do attempts for solve, and you can do real solutions. It's a lot of fun. Now, doing microcorruption in microcorruption, super fun. Doing microcorruption in Radare2, ultra fun, obviously, right? So what we're going to need to do to bring that into Radare2 is some kind of utility functions that can help us load disassembly that looks like this, and the memory dumps that come with it that look like this into Radare2. And Radare2 actually knows how to deal with iHex files, which are this way to capture data as well as the address of the data in one portable kind of thing. So we can actually load that up. 1 second here. Right. So friend, Atlas of Doom, awesome guy. He put together a bunch of utility functions that allow him to use those copy and paste out of microcorruption and create these Intel hex files. And he did that to use with his favorite tool, which is Vivisect. But this is not a Vivisect talk. We're going to abuse all of the awesome work he did for Radare. So we put that together. There's a way that you can just give it the kind of copy and paste, the ASM and the mem, and then you give it a name, and it'll create that hex file using Intel hex and some bin ASCII logic. It'll parse through the lines. You can see there's a lot of kind of crappy Python, which is the Python that I'm best at, for sure. And same kind of thing here. What we're going to do is look at the disassembly and pull out the functions that we want to define. So we're actually going to create radar flag lines. We'll learn about flag lines a little later, so you can see them here. So we're defining locations of things in that disassembly, because you'll notice the disassembly actually includes names on particular lines, like low level init. And you can see some more juicy names up in some of the levels. So after we put all that together, and remember, you can download this Python. I'm not expecting you to read it. You can download the notebook if you want to use it. We are able to go ahead and load up the tutorial level. So I got this block of text by going to microcorruption, opening the tutorial level, selecting that whole memory dump, and pasting it here into that string block, and then doing the same thing here for the ASM. And then what we're going to do, just to make things a little easier later, we'll save those into files. Remember, I said this is crappy Python, not good Python. And we will use those files in a second. So I executed that. And then we can load up the whole thing as a Radare2 session using the stuff we just kind of browsed over quickly. And then we'll run which is default analysis. And then we will print disassembly of a function at the entry point. So that's the way the Radare command goes for printing disassembly. And a lot of the mnemonics in Radare are kind of based on like a tree of what you want to do. So all the prints start with P, all the print disassemblies start with PD, and then printing disassembly of a function F. So let's go ahead and do that. I forgot to define the functions again. Still forgot. Back up. Someone at home who's following with the Python notebook has actually done this correctly. You beat me to it. So here we go. Assembly done, and then we get like really lovely colorized disassembly, which, if you're anything like me, definitely helps with analyzing what the heck is going on. And immediately we can see, hey, there's a reference to an invalid password being moved in R15 here, and then a call to puts. So this is obviously printing invalid password at this location in this assembly. It'll only do that if it jump not 0. So if R15 is 0 after check password. Wow. So this is like a straightforward crack me, and we can probably figure out what the heck we need to do. So why don't we go ahead and do that? Let's do a manual solve of the first level. Now, before we actually do the manual solve, I just want to take a look at chat and make sure there isn't any questions about what we've covered so far, because we're going to start doing more and more Radare, and it won't get less Radare-y after this. Okay, no questions. Excellent. Let's press on. So as we mentioned, that invalid password is getting printed if R15 is 0 after calling the check password function. So why don't we look at the check password function? So we know that analysis, the AAA command, has actually defined all the functions for us. So we can print disassembly of a function, PDF. This at command is a temporary seek. So we're asking Radare to temporarily seek to the address, which is flagged as lock check password, and then run the PDF command. So if we print that up, we can look at that for a second. No cheating and reading my analysis below. You can see here that it's doing a loop. Radare does this handy thing of printing these little jump arrows, which you get in IDA and other disassemblers do. And it is incrementing R15 and R12, and then testing R14. And it's moving something from the address of R15 and R14. So it's counting the number of, this is a pointer moving up, R15, and this is a counter getting incremented along with it. It will jump away when it finds 8 things. So therefore, any 8-character string will solve the challenge. Right? Which is cool, and we did it. But this is tutorial level, so we're really demonstrating Radare's capability, not that we're amazing reverse engineers, which I'm sure we all are. Let's talk about anger. So this is something I found really interesting. There's a lot of really great work by a lot of really smart people, and we can actually stand on their shoulders to start solving microcorruption challenges automatically. Anger is actually symbolic execution, which means It stores a complete state of the processor that it models, and it can actually store the equations that transmute or the transitions of those states in an analytical way. So it can use solvers like Z3, for example, which is integrated in here, to answer questions like, what kind of input would I need to actually get the execution into this particular state? Because it's symbolic, it's analytical, and you can actually unwind execution that way. All right, so you can learn all about Anger at anger.io. Here's a screenshot of their homepage. Anger comes with support for a lot of different platforms, but obviously there are other platforms we want to use that are weird, like MSP430. And these amazing people here made the Anger platforms collection, which includes some weird ones, but more importantly to us, MSP430, which is what microcorruption uses. And in fact, in the Anger platforms test suite, you will find microcorruption challenges. So they were using microcorruption to put the Anger platforms together. And then even better still, this person, Watang, put together a loader that uses those two copy and paste that we just talked about to build little Anger projects. So you don't have to do all the backflips of putting together the processor memory layout and patching the return from the system call handler and all the little stuff. It's all wrapped up together in that nice little package that's super easy to use. So let's look at what a solve at that first level would be using this framework. Right here, there's this Python notebook kind of magic that you can use, the double percents, and I've commented it out, but if you uncomment this, it will capture all the print outputs, so you won't get a lot of noise. Anger is quite noisy to standard out and standard error when you run it. So we're going to use that microcorruption loader that we just talked about. It is smart enough to use copy and pastes of the memory dump and the disassembly windows for microcorruption. That's all you need to give it. So what we ran above, where we created those two writes up here, that's all you need to prepare the microcorruption loader, creating those two files. Back, we're going to make a simulation manager. This is the way that Anger kind of tracks all the different state spaces that are possible. We're going to ask the simulation manager to just go and explore for any execution paths that lead to the final symbol of unlock door. So if we went back to the disassembly, you'd see that unlock is what's run if you get the correct password entered. And then at this point, we're going to turn the symbolic into the concrete, and we're going to ask for what was the actual input that would have given us the execution that led us to that unlock door. Right? So this is kind of like reversing backwards in the CrackMe, where you find the win function and then go back to figure out what brings you to the win function. Except we're not thinking about it, we're just kind of running code and it works. So why don't we do that? So you can see Anger and Anger platforms doing some stuff, loading up at the addresses. You probably recognize those from the mem dump. It does do automatic recognition of some of the symbols in the disassembly, and some of the things actually get hooked automatically. So when you're thinking about symbolic execution, not everything can be executed symbolically. At some point, you need to actually like lift and perform operations in the virtual machine and then kind of tell Anger that you've taken care of it. It can't handle the entire possible space. And this is common for even when you're running on Linux, not just MSP430 bare metal. And you can see that it's recognized where the weird functions are, and it's actually hooked them already, so it knows that the thing that you type into a microcorruption is actually, you know, an input function, and the thing that comes out for the I/O is an output function with puts. And that's good because that lets you use the normal Anger stuff. So what is it? There you go. So this is fun. There must a little race. Usually it shows all Fs, but you know what we're learning here, because all we knew was that it had to be an 8-character string. Anything is valid. The solver is happy to send in, you know, almost all ones, 8 characters. And microcorruption does allow you to put in hex encoded strings. So this actually is a valid input that you can stick in. And if you have an account or you have it open, go ahead and confirm that now. Alrighty. So we don't have to stop there. We can go to the second level. The micro-corruption loader package that we talked about from Whatang, it actually has a few different solutions in it. I've been working on some as well. I've gotten to the point where either the loader or Anger itself kind of craps out and doesn't yield solutions yet. So it doesn't take you all the way there. I'd love to figure out why. The micro-corruption levels are all named after cities. So the next level is New Orleans, and you can see we've done the same thing. Copied the disassembly, copied the mem dump, and we're going to write those in the files. All right. Now the solution, because this is automatic solution, is pretty much the same. We've just changed the files. We've asked the simulation manager to remember locations where it kind of goes off the rails. So unconstrained states are execution states that could explode exponentially into all kinds of possibilities. It tries to trim those, but in this case, we want to keep them open. And then, yeah, we're trying to find that unlocked door location. And then we're going to convert the analytical or the symbolic into the concrete. And the errors are actually normal. All it's saying is that, remember, the micro-corruption loader is the thing doing the hooking. And the loader has tried to automatically create hooks for these two things, but this particular level doesn't have them in this assembly. But it's not fatal because, as you can see, we got a solution. And it's gobbledygook. Now, that hardly seems like valid input for this challenge, but if we go ahead and reverse engineer the check password function, we'll see why it is valid. So remember the as R2 function we put together. This is how we can get an R2 session or load a micro-corruption level into Radare2. We're going to do that. We're going to run analysis on the whole thing. AAA is default analysis. And we're going to do a temporary seek to check password just like before, and we'll print it. So, but unlike the tutorial level, this next level has a slightly different disassembly. There is a jump out after 10, or sorry, that's not 10, that's 12. And you can see that it's still tracking. There's a comparison directly here with an offset. But that's why it's a valid input. And you can go ahead and test it yourself if you want to have option open. Remember, there is a hex encoded input that you can give. Right, so that was the warm-up. We were looking at micro-corruption as the easy step up. Remember, this is really about Super Nintendo. I think I put that in the description. I love the Super Nintendo quite a lot, and I was really, really happy when Zach from NSEC put together a challenge last year that was based on Super Nintendo. I remember my friend Jonathan Beverly and Colin DeWinter, they IM'd me. We're on the same CTF team. They said, "Hey Ben, do you want to reverse engineer a Super Nintendo challenge?" And I said, "I've been waiting my entire life for someone to ask me if I want to do a Super Nintendo challenge." It was just the best thing I'd ever heard. So it was super fun during, and then, life got lifey, and I didn't really do the write-up when I was supposed to, but I did eventually get around to it, and I decided to do it in this Python notebook format. So you can actually find like a way more detailed version of this in a Python notebook gist also on GitHub, but we're going to walk through it. Now I realize I'm getting kind of old. There's probably people out there that don't know what a Super Nintendo is, so I have to actually tell you what a Super Nintendo is. And the short version is that it is actually the best video game system ever. Apologies. You can get a great overview of it at the Super Nintendo programming wiki book here, which I'm showing you a screenshot of. This is really useful when you're trying to reverse engineer as well, because it has a lot of memory locations that you're going to want to have. So this challenge was a crack me, and Zach put it together so that you had to figure out which buttons you needed to push on the Super Nintendo at particular sequences. And it turns out that the button combinations you needed to push were actually frame perfect. So you had to have frame perfect. So if anyone's into speed running, that's like a big deal. Frame perfect inputs to get the flag to print out. Here's a screenshot of when I I figured out the first correct input, and then you hit start, and it only prints out this one fragment. And of course, I tried to submit this flag, and of course, it was not a valid flag, but you have to try. Right, this is a frame perfect trick. This is a frame perfect Super Nintendo CTF challenge. And you have to submit everything as a flag, but that wasn't a flag. But we get these two descriptions, right? Now the theme of the last NorSec CTF was kind of like this D&D world, and you're at the Black Cat Tavern, so everything has like this alchemy kind of feel to it. And we were trying to figure out what is the correct sequence. So we knew that we needed to put in a button sequence, and we knew that it was a Super Nintendo ROM because SNC, and they all come with an emulator. And they tell us to use ZSNES. This was a good tip because it really didn't run in anything other than ZSNES. And this is a photo that I took of an old Windows 7 laptop that I just had ZSNES on because, like I said, Super Nintendo is the best video game system ever. And then there's a second sequence that gets a little bit crazier. But spoiler alert, we're going to do the easy way to solve sequence 2, and we're going to do the hard way to solve sequence 1. Because this isn't about the CTF solution, this is about learning how to use Radare2 to solve this thing. And yeah, as I mentioned, what we're going to be looking at is really in detail here in this gist. The next stuff is going to be me talking about it instead of all the writing. So if you go to this particular Python notebook, you could just read what I'm saying for the most part. And here I'm going to be doing some talking. So yeah, sequence 1. We need to find those correct inputs. We're going to do it the hard way, which is reversing by finding where the joypad is actually written, or joypad is read, and then following execution from where the joypad inputs are read to where the flag is printed. And that's, in general, in a CrackMe, that's going to be harder to do, more time anyways, than going backwards from where the flag is printed. So we're going to follow a sort of a plan. We'll find where those Super Nintendo joypad inputs are. We'll find what's accessing those joypad inputs. And then where's like the good, bad decision on the inputs? Where's the comparisons that are deciding what's a good input? And from that, we'll be able to figure out what are the actual inputs it wants, right? And then from that, we're going to press those buttons, and we're going to print that flag. All right, so why don't we start with that? By now, you should recognize this is opening a particular file. The -2 argument just tells Radare to close standard error. The Super Nintendo kind of analysis engine, I want to say plugin, it's not a plugin, it's part of libr. The Super Nintendo part doesn't interact very great with Radare, and a lot of warnings will get printed, so we're just going to close standard error. If you want to look more at like where the warnings are and what's being put out, you should remove that argument to R2 open. Okay, so we open sequence 1. Why don't we use the Radare I command, which is information. So it'll tell us some info about the container that we gave it. And you can see it's got a lot of different fields, so it will recognize endianness, if there's line number information, what operating system it's for, etc. When I see a big printout like that, especially during a CTF, my eyes kind of glaze over, and this is a great way to demonstrate that Radare has a built-in grep command, which is the tilde character, right? So we're going to use the built-in grep plus for case insensitive to filter for anything NES, just to make sure, like, does Radare even know this is a Super Nintendo ROM? And in fact, it does, which is fantastic. All right, so we want to go from the joypad inputs to the flag. So are we lucky, and does Radare have like a built-in table of all the joypad registers? Because that would be fantastic. Radare, for memory locations, uses what it calls flags. Not those flags, sadly. So the flags are all accessed by F. So why don't we grep the output of all the flags it knows about for joy? But no joy. That's okay. Remember, we gave you a link to that Super Nintendo programming wiki book, and some Googling found this almost immediately. And what we can do is copy and paste some of the information from that wiki book and create a sequence of our own flag definition commands, right? So first you put in F with no arguments prints out all the flags, but F with some arguments starts defining them. And we can say these are all 1 byte. That's probably inaccurate. I think in some cases they're 2, but we're not super interested in the width of the flags because the data analysis doesn't work perfectly for this architecture anyways. And then we have the address and then the description of the name. So when we run this, all of those locations in the memory space for Radare session are actually now defined. And if we print out all the flags in grep, we can see they're defined correctly. This has some nice side effects when you define flags. So here what I've done is I've done a print hexadecimal with comments, so PXC, 16 bytes at joy1b. And you can see that Radare adds as comments that this location is joy1b. So when you add flags and you do some disassembling or some hex printing, you'll get the nice markup of those locations, so you don't have to remember that 4218 is in fact joy1b. You can see it when you do the printing. This one here, PXA, is print hexadecimal with annotations, and it does this really nice kind of call out style for flags. So it does unfortunately mask joy1b, but you can see exactly where joy2a is. And this is useful to demonstrate what the flags mean, because we're not actually like emulating this or connecting this to a debugger. We're not going to be able to see the contents at those locations. What we would like to do is see those locations show up in the disassembly. So let's move on to that next step. Radare has this concept of data references or cross references, and this isn't unique to Radare. All disassembly tools like IDA and Ninja and all of them, they all know about cross references. And the cross references are really, they're what let you win with disassembling. It's how you can tell what's being referred to, what's being called, not just where execution flow goes, but also where the data references are. The access to these cross references is using the A for analysis, X for cross references command. So we can have it list all of its cross references with AX, and then we can grep them once again for joy. So we're asking, now that you've done the full analysis of the binary, because we ran AAA, actually, sorry, we haven't done that yet. We'll just ask if it knows cross references. No, it doesn't. And are any of the cross references you know about data at all? So when you look at a cross reference, it'll mark it as code or data, so you can grep for just the data ones this way. But of course, and I kind of gave that away, we haven't run analysis yet. So let's run default analysis. AAA, you saw, was pretty quick on some of the microcorruption binaries that we had. It gets pretty long on other things, particularly on Super Nintendo ROMs. There's a lot of stuff it does. Most of it, sadly, isn't as useful as you want it to be. But this particular write-up is really based on default analysis and not on some of the faster forms. So this is definitely not the coolest way to run analysis. There are faster ones that are more targeted. So if you look at the AA question mark command, you'll see a lot of different options just for like detecting the signatures of the beginnings of functions, and also for just analyzing only through call trees. All right, so that finished. Now we are equipped to instead do some disassembly of the functions. So AAA, default analysis, is going to mark all the functions that it finds. And when it finds a function, it's going to create a flag, and it's going to prefix the flag with FCN to make it known that it's actually a function. So what we can do here is use the iterate command. We previously ran into just single at. Single at is a temporary seek. Double at is run this command on everything that matches over here on the right. So we're asking it to run PDF on every function. And then we're going to grep that output for anything that includes 4016 and 4017. Okay, so why are we doing that? Those are the old status registers. Super Nintendo has two different ways to access joypads. So we need to figure out, are we looking at a Super Nintendo ROM that uses old style joypad access or new style joypad access? So let's check for old style first. No accesses at all, right? So the output without the grep is really a disassembly of every function. So it's a pretty decent fidelity way to look at a disassembly of the whole ROM. You're not guaranteed to jump into the right locations and have like a perfect disassembly, but it's probably going to be okay. And then we're grepping it for those two locations. And since those different locations never showed up, we can say that with good confidence that it doesn't access the old joypad locations. So let's look at the new ones. The new ones are defined by these four addresses. There is a bug that we're working around. Yeah. So I did this. I noted some bugs to myself as I went through. I'm hoping to do some improvements. I did add these. I did get permission to add these binaries to the test bins. So there's no reason why I shouldn't be able to. And I did try to do some bug hunting. Hopefully, if we have time, we'll get to that at the end. But spoiler alert, it's not an actual bug, so maybe not. But anyways, doing the same thing, disassembling all functions and looking for references to those new joypad locations. But we can see that there are actually reads of 4219 and 4218. Now, I had promised that we would get nice comments on locations. And in fact, it would be even better if in this disassembly it said joy 1B at this point instead of showing just the address. The bug here is that the disassembler for Super Nintendo doesn't turn these reference addresses into flag names for things like LDA. It will for the LDX instructions. So this grep worked because there are LDAs that refer to those joypad locations. But anyways, we can say with some confidence that it is using the new joypad locations. All right. So the natural question is, are all of these locations, these three here, 81E2 through 81E, 81FF in this list, are they all in the same function? Okay. So what we can do is seek to each one of those locations, and then we can do a seek to the top of the function. So that's what this is. S is all the seek commands. SF is the seek function command, and it's seek to the beginning of the function here. And then $V is how you print out current values from the variables that Radare has. $$ is the current location. So we've asked Radare to go to the particular location it found, go up to the beginning of the function, and then print where the beginning of that function is. And we can see that in all three cases, that shows up in 81D3. So good news, all the joypads are being read in one function, which does make our life easier since we're trying to reverse forward. We only need to understand that one function. So let's add a little bit of kind of sugar to our disassembly so that when we disassemble 81D3, we're going to notice where the accesses of the joypads are, because there's this bug where it doesn't print the things for us. If it happens, we need to actually figure this out anyways. So here what we're going to do is we're going to add a comment, which is this capital C. We're going to add a comment that says joy1A, and we're going to do it for each location. So here's another type of the iterator that Radare has. Notice it's got the equals on it this time, and then there's these backticks. So if you've done any like bash or other shell coding, not shell coding, coding in interpreted shells like bash, you'll know what the backticks is. That's an evaluation operator. So Radare has its own, and it is able to run Radare commands and then turn those into strings. And so it's running a comment to add joy1A to each of the things, each of the tokens that's put out by what's in this backticks. Let's talk about what's in the backticks. Here we're doing another disassembly. The PI form is like an instruction style disassembly instead of the really sugar one, so it doesn't have all the lines and annotations, so it's a little bit faster. And we're grepping for all the places that it is referring to 4219, which is the joy1A register. This square brace 0 is how the built-in grep can actually parse out columns. So a lot of people do this with cut or awk on the command line. In Radare, you can just do it in any grep. So we're grepping for a thing and then filtering for the 0th column. And because we're using PID, the 0th column is always the address. So we're making a comment that says joy1a at each of the addresses that contains a reference to 4219. So these things up here. And then this pipes trick here is so that we don't have double comments. So we're just sorting and making it unique. I probably could have done -u to be really quick. So there we go. Let's get those comments in. All right. Now we know where the code is accessing the joypad registers, and we marked them with some sugar, so they'll show up in our disassembly. And we need to keep following that data flow forward. That kind of process generally is kind of like browsing, and if we weren't in a Jupyter notebook, we probably would open up visual mode in Radare, which is capital V, and then we could page around in the disassembly, which is great. You could also do like PDF to print large functions, and then if they flow off your screen and you want to look at them, you can use built-in grep. So tilde ... which is the built-in pager. So you can just page around, but we're scripting this stuff in the Jupyter notebook. That's not really useful to us. So let's start by dumping the disassembly of that whole function. It's the 81D3. But we're going to do a little prefix of a command here. So we're going to add more width for the jump lines because there's a lot of jump lines going on. This is going to be pretty big. So we're just going to scan over it and only really look at the parts where we have annotated with the joy comments. So this is the full disassembly of 81D3. We made it nice and wide so these jumps would show up. And you can see here's the 3 locations where the joypad is being accessed. So we have these LBAs here. There are locations where they're being jumped away from, right? So this is jumping away from that read if some kind of test is being done. We'll look at that. This one here, loading joy1a, could be skipped over if there was some test here. joy1b, that one seems like it would always happen if this one happens. Okay. So we've marked that up. We kind of understand this function is doing stuff at the top and then some more stuff with that stuff at the bottom. Now, there's really only 3 places, maybe 2, where the joypads are being read. It would be really nice to focus in on those, and we don't really have paging as we're in the notebook. R2 has this way to do disassembly of just the basic blocks. So when you're doing disassembly, a basic block is a continuous section of code that doesn't have a branch or a test in it. And these basic blocks are kind of, if you look at disassembly graph views, they're the boxes in the disassembly graph view. So what we're going to do here is try to get all of those locations that are accessing one or the other. So you recognize the PID, grep, filter, column command here. FB is a special variable that'll show you the address of the start of the basic block. And remember, $V is printing that. So we're printing the start of the basic block for each of those locations that refers to those. So we can see what are those basic blocks. So these are the basic blocks where the joypad is being read. Why don't we go ahead and just add some flags to those so we can refer to them later or see them in our disassembly. That's great. And then let's look at that first basic block. So here, it's reading joy1a, and then it tests if a single bit is set, bit 8, and then it jumps away if it's set. And if we look at that programming manual, we'll see that bit 8 in that particular register is the start button. So that branch, the BNE, is going to jump if the start button was pressed, which means let's note that as press start to jump. And then we'll call the true target start is pressed, and we'll call the false target start is not pressed, and then we'll do a reprint. So you can see our comment showed up, and our sugar is working. And let's continue. So the next obvious question is, what happens if you don't press start? So R2 is going to let us query destinations of basic blocks with that FJ. What address does execution go to if it's not pressed? So we can say show me the value of the false target if we're at that particular branch, that particular basic block is 819E. Okay, well, let's look at what's in the basic block at 81E9, and that's that location where we saw that pair of reads. So more joypad location checks, which is great. So we can see that there's a joypad, joy1A value that's read. There's also like a derivative value that's stored here in 121C. Similarly for joy1B, there's a derivative value that gets stored in 1220. And then there's later derivative values too, 1218 and 1214. So there's something going on with two kind of cached values of those joypads. Why don't we add flags for all those cached values and just look again so things will get a little clearer, hopefully. So what I did there was I'm running these flag commands. We're adding some comments. So this is really extension of the pattern we've talked about before. And then we're going to reprint that basic block. Okay, so now we got lots of nice comments. And you can see there's some XORing with one of the cache values and then an ANDing, store, and then load, store. So it does look, and I hope this is something that can be grepped by others, that it's doing a test to see if the button state changed. All right. And previous state. So let's run those. What we're doing here is disassembly of all the functions. And now that we've marked everything up with comments where they're accessed, we can now grep for disassembly of all the functions for the comments now that they've been marked. And we're turning off the ASM lines because the ASM lines, you might remember, are these things on the left, and they'll kind of mess up the output and make it hard for us to see what we're looking at. So this pattern here is us grepping through the whole Super Nintendo ROM, looking for locations that are accessing these cached values of the joypads. And you can see there's definitely some places where 0 is stored into them. So there's like an initialization location. There's the loads of them. And then there's the store and EOR that we saw before. And each one of them, cache 2, has a similar thing. There's loads as well as stores. And then there's a false match here. And that's going to keep bothering us as we go through the disassembly. So we have to learn to ignore this false match. We don't know why it shows up, but these things happen. So, and yeah, let's look at where those STZ instructions are going. So the STZs, 8047, 8048, why don't we print the basic block of this particular store Z? So where's the store Z happening? Oh, no, I'm jumping ahead. Sorry, I got out of sync. We are looking back at the second joypad check just to confirm that that's where those exclusive ORs are. So the exclusive ORs we saw in the full grep of the Super Nintendo ROM, what's happening in what we looked at already, where we had those second checks. The start is not pressed location. And we could look at where cache 2 is accessed similarly. So the cache 2 values also have that same kind of pattern. And then we can go back and look at that STZ. And the STZs are unsurprisingly happening in the initialization of the Super Nintendo. So those cache locations are getting stored with 0 as part of init. So what we want to look at instead is the read locations of the cache 2 globals. Those were all the LDAs that we could grep out above in here. Those cache 2 globals seem to be the locations where maybe stuff is happening because the cache 1s didn't yield a lot of information that they were being tested for button change. So we're going to do that by doing doing a PDF, so a disassembly of all the functions, and then we're going to grep for locations that are referring to the cache2 values. We're not able to do the column grep trick when we're running it on these commands, even though it does work on this form here. It doesn't seem to work on this form here, so we're going to shell out to grep and awk and sort to accomplish the same function. Okay, and that's going to show us only the LDAs of the cache2s. Now, something is going wrong here. We're only looking at the entry point as the only result we got, not an actual address. So what we actually processed in the list before we tried to print out that basic block was this, which is valid addresses to be sure. But as soon as we stick that into this iterate equals, something goes wonky, and it isn't really clear what. But what's important, and I want to give to you as a trick, is the workaround is to put all that into a file, so just a temporary file, and then you can use the iterate over file command to read it in and accomplish your task. So not sure why it happens, but this is kind of how you can work around it. And it shows us that there's a lot of basic blocks where these read accesses are happening. Okay, so what about functions? How many of those basic blocks are in the same functions? Lucky for us, it's only happening in one function, and it's that same function we saw before. So it's that one big mother function. It's not ideal because that is a big function, but we can figure it out. So let's look at just the disassembly of the basic blocks that are involved. So remember, we stored those basic block addresses in this file. We can iterate over each line in that file, print out the locations of the start of the basic blocks. We'll put that into a file, and then we will print disassembly of the basic block for each of those addresses. So we're just doing the disassembly of the basic blocks that have loads of the cache2 locations. Okay, looking at that disassembly a bit. If you take a look at it, I know it's quite a lot, especially for a stream, you can actually categorize each of these into either a test that jumps if the button is pressed, or a test that jumps if there's no press, and then there's these two other tests that use TAX and XOR, so EOR. It's not clear what those are doing yet, but let's get back to those. For now, what we can do is label the ones we do understand. So you can see we're kind of categorizing, right? We're going to go to this one location, A2CA, probably one of these here, A2CA, this one right here. So going bottom up, and we're going to say that is a jump if button is pressed test. We are going to add a flag. The E version of adding a flag will add a dot number afterwards, so you can actually have the same thing over and over again, and it'll automatically increment the number on each of those flag names for you. And we're just going to do that and categorize each one of those locations. So you can see the locations we know, we're categorizing them as either jump if button pressed or jump if no button pressed. And then the four something else's, we don't know what they are. And then we'll go ahead and do the disassembly of the basic blocks once again and have a look. So here's the jump if no button pressed. Here's a no button pressed. And here's a jump if something location, so we're not really sure what's going on. The breaks here, so there's no line breaks given in between when you iterate PDBs like this. So you can tell the PDB is over because basic blocks end in a branch. So this is the end of a basic block, and this is the beginning of the next basic block when you're doing this kind of an iteration. And that's the end of the basic block above. But you can see we've categorized everything. Let's look a little closer at those other categories, the ones we didn't know if it was a button test or not. And we can do that because we categorize those with a flag. we can use that iterate operator on all the flags that match jump if something. So that gives us 4 basic blocks to look at. In all the cases, that cache2 variable, which only contains the newly pressed buttons, because remember, and I think I might have gone a little fast over that, but in that big mother function where it was looking at those 2 cache variables and doing the XORing, it was detecting buttons pressed, and cache2 only contains the difference of the button state register, so it contains the newly pressed buttons. In all the cases, it then uses a TAX instruction, which is going to copy the value from the accumulator A register to the index register X. And then it does a bitwise exclusive OR with something and then or sometimes an AND. So it's either an EOR or an AND on the result. Now, to actually figure out what's going on there, you want to have access to this table that shows you what the bits in this joypad registers mean. And I've kept that here for reference. And I've kept this here too because I want you to be able to read that and understand it as opposed to me reading it to you. Right? So these are the locations where the code is actually testing for the button values and then doing a jump if the button value is correct. So we could look at even just the last one here, this 1218, which is doing an AND with 2 in that location, O2C3, which means it jumps if at least the L rocker button is pressed. Okay, so we can decode all of that, and we figured it out here. Why don't we turn what we've learned into some more flags and comments, because that will make our understanding easier, and then we can look at all the EBBs, all the basic blocks once more in the disassembly. And you can see we've now marked it up with stuff that makes it really easy to understand. Press L to jump, press only Y to jump, press select and up to jump, so we actually understand what buttons need to be pressed. And this is the frame perfect part, right? You have to actually press those 2 things together in one loop of this polling function for the flag win functions to get executed. So now that we've figured out what the joypad reads and values are that are necessary, we want to go back and look at the disassembly of the big function so that we can make a little more sense of it. And we're going to start by disassembling from that first joypad check and then kind of moving onwards from that first joypad check. And luckily, we've created a lot of comments and flags, so things are going to be much more readable this time around. So what we're doing here is a recursive disassembly. So this is print disassembly recursive, and the dot is for the current location. The current location is actually given by this temporary seek, because we use the temporary seek command at. So we're doing a recursive disassembly from the first joypad check location. So we have all this nice annotation. This is the press start to jump location, which means we're going to go to A213 if we press start. If we don't, we're going to do the second joypad check. We probably recognize this block now as doing the store of the new buttons. And if we did all the correct button pushing, we will be able to push start later, and pushing start will take us to, we just set it, A213. Oh, that's a loop. And away we go. Well, I guess I said it would be a lot more readable. I think it is a lot more readable. It's just not fully grokkable at this point. But what we can do is start looking at what happens when we get a recognized joypad press. So let's scan it over. It's quite a big function. We have another bug here. We should be able in Radare to just do this at and match, but it looks like matching the star first doesn't necessarily work. So what we can do is grep the output of all the flags, put that in a subshell, an eval expression, and then iterate over all of them that come out of it. And what we're asking here is, what are all the paths that are taken when one of the joypad presses that we've recognized, remember we flagged them with is pressed, happens, and we're just printing the basic blocks. So we can see that there's a store into index to the X register in most paths. These are storing copies of those joypad caches that were made. And why don't we label those locations and add some comments for access to them. And we'll also label the jump targets. So you can see these are jump targets. That this is a very small basic block. It does one thing and then moves on. So it's pretty easy for us to actually label what those next jump targets are as well. So we've decoded that, made some commands, put some details in. You're going to see the same pattern again, where we're going to grep through the function, looking for all the places, grep through the disassembly of all the functions, looking for all the places that are accessing particular addresses and marking them up with comments. Remember, we're doing that because the disassembler isn't really good at putting those names into the disassembly. So let's run all that. That shouldn't take too long. There is a bunch of iteration though. All right. And then we can go ahead and do a disassembly of everything and grep for all the locations that are now accessing those pressed caches that we're calling the 12, 1204, etc. Okay. So we got one false match. Again, I think we talked about that rep 30. There's not a whole lot we can do with it. We can even try to remove the comment at that location. But even though we've done that, it's still gonna kick around. So we'll just forget about that. Otherwise, the pattern is pretty clear. Other than the store zeros, it's doing a load and store in the index register. So you can pairwise load, move to the index register. We can look closer to the locations where those globals are accessed by disassembling the basic blocks that are used for each, right? So we need to work around that small bug again, means we have to put everything into a file. But otherwise, it's the same pattern. Disassemble all the functions, right? Grep for press cache, pull out that first column, right? And then grep for the particular addresses we're interested in from up here, because there's a lot to deal with, right? So we're going to remove the 8360 false positive, and then we're going to remove the 8000 init function. So that's what the grep v's are doing, taking those out. And then we're going to do a disassembly of the basic blocks from each of those locations that we just saved. Okay. So it sure looks like we assumed, right? All of those ands of the FFs and the branch if equals are testing for any key press. And the joypad registers that were stored in the press cache is where it's getting stored when we get down to this point. There are some invalid instructions that show up here. Actually, that's the bug that we investigate later, so we actually know what the reason is for that now. But at the time I wrote this, I wasn't sure. There's some stateful disassembly because Super Nintendo actually has different addressing modes, so it's not decoding this stuff correctly because it's in the wrong state from executing. But we know how to fix that if we have to. Right. So compare the. We don't need to do that. Yes, very good. So forget about those bad instructions right there. Good. Let's disassemble again recursively from the start is pressed. Remember that thing where it's checking where we do the start is pressed. And then we're going to filter out the first column. That's where we're going to seek to, right? So we're going to that location. You can see with this, the recursive disassembly is showing you that you have, I'm getting a little lost actually. Let me read my notes here. Yeah. Okay, so this output here is quite lengthy. It's meant to just kind of be scanned over, and we're looking for the axes like this one. So you can see there's loads of these locations, 884B, that are indexed, right? And it's over and over again, 884B with an indexed access, which is, like vector or pointer math. And that address, that's actually quite different from the other addresses we've seen, right? A lot of the things we saw were 1200s or 20s. Remember, this is hand coded, so it's put together kind of logically, not by a linker. That 884B that's being accessed by index operations is pretty suspicious. Why don't we do a print hexadecimal with annotations of that location? There we go. So following that data flow down to the point where if the buttons were pressed correctly and you press the start button, you can see that there's indexed accesses into this flag register and then presumably followed by some kind of printing when the function exits. But this flag isn't quite a flag. So let's flag the flag, which is telling Radare to mark the address. And then let's look a little closer at it. I should note that as soon as I saw this, I did actually try to submit it as a flag to the scoreboard, but it wasn't accepted. You have to try anyways, though. So let's look at that disassembly a little closer at the location that after start is pressed. So index register X actually is initialized with 0 and then used as an offset to copy out 5 of the bytes from the flag buffer. So this particular basic block is printing out flag dash, right? Is that's the first bytes. So we found the win function. If you're doing crackneys, this is the part that prints out the flag. This is the part you want to get the execution into. The catch is that we could have actually found the win function by going backwards from flag, like by doing a search and submitting it. But that's not a flag function all by itself. This flag is not the whole flag. The catch is that this Super Nintendo ROM is using values from those cache, the cache locations of the joypad registers to actually index into the flags. And I'll show you a little bit more what I mean. So let's look a little closer at the next EBB. So index register X is getting loaded with the value from 1200 after being the Y is being 0. Okay, and then we know it copies out 6 bytes from the flag buffer starting at the offset, starting at offset 40. 40 in my notes, but I don't see it clearly right now. I think we know 40 from the previous value. Yeah, right. 40 is the correct value for the Y pressed cache, right? Y is hex 40. Okay, so it uses the offset, uses the correct value of the pressed cache to look into where to start the copy of 6 bytes. This is an anti-cheat technique that you might find in video games. It's called data entanglement. At least when I worked at Radare2, that's what it was called. It's like a control flow protection mechanism. If an attacker was to patch this binary and just jump control flow, jump execution straight to the win function, then what gets printed out is a nonsense flag because it doesn't have the correct values for the contents of these caches, of these locations in the joypad register. So you have to push the correct joypad inputs to get the right values into these things to have it read out the correct bytes from the flag location. Now, which I did. The first thing I did was patch the binary and just go to the win function, but of course it prints out garbage. Now, we could actually, continue to get all the segments. The next reads are of 5, then 5, then 10 bytes from the correct joypad locations, which are hex 84, hex 28, hex 20, and then the 2 that we talked about before. And you can actually do this in Radare, right? So we can print 5 from the 0 offset of the register, we can print 6 from the hex 40 offset, and so on, to actually print the flag, which matches the correct flag from the screenshot that I have, and yay, we won. So remember, this is an exposition of how to use Radare2, not necessarily like the best way to solve this challenge, and we didn't actually have to go this far. By the time we had actually decoded valid inputs above, we could have gone to an emulator and just stuck those valid inputs in using macros in the emulator to make sure they're frame perfect. And then we could have got the flag output here, which is what I did here in SNES the other couple weeks ago to get this screenshot. Incidentally, getting this thing to run in SNES requires spamming reset just to get it to load. So I was pretty lucky to even get it to load to do this run. But we did this to learn R2. Yay for us. Now I do have a second write-up where we reverse backwards. This is actually the easy way to do things. Let me just check on chat, make sure anybody has any questions about what we just did. The Python notebook is available online. You can download this and run this yourself. Okie dokie. Excellent. Why don't we reverse backwards? Or wait, I see Garth. Is everything okay, Garth?
Everything's fine. I was just checking in.
All right, cool. So we're going to try reversing backwards. This is with sequence 2. We're going to open up the file. We know that it understands Super Nintendo by now. We know that it knows the container. So this is kind of the natural way that you'd attack a crack name. Let's see if flag is in the binary. In fact, it is. Great. All right, that should make our life easy, right? So flag is in the binary. When we search in Radare using this slash function, everything that it finds is marked with a flag, and you can see that here. So it marks it with hit hex _ y. This is our first search, first hit, so hit 0, 0. What we're going to do is first remove that flag and then rename to flag. And then let's just do a hexadecimal print of 32 bytes of that location. You can see, in fact, flag has flag in it. Good. Now we have to do some analysis. And again, AAA default analysis takes some time. So here's a funny picture while we wait and while I drink some water. And we're still waiting. Only one funny picture this time. I think streaming must load my computer down, so it takes extra long to do automatic analysis. So we're going to follow the same pattern of disassembling the whole binary. So finish there. So this is function disassembly of every function that's now been recognized. And remember, there's a bug in the disassembler for Super Nintendo for indexed load instructions. It will put the correct flag name into the disassembly, and for non-indexed into the accumulator, it won't. So we're going to grep for both flag and the address. And doing so shows a few locations that are definitely accessing the flag register. So we're going backwards now. We're starting from flag. We're looking at the locations in the code that are accessing that flag buffer. And then we're going to go back to how does the code get into the code locations that are accessing that flag buffer. So let's grep through all the disassembly to look at all the EBBs that are doing indexed loads. Because remember, we know that the win function is going to be doing data entanglement. Again, they did it in level 1, so we'll do it in level 2. So yeah, let's find all those index loads into flag. So this should be patterns that we recognized from before, right? There's some, this time it's using a compare 5, then 6, then 5, then 5, then 10. We don't know what the offsets are because we're looking at the basic block where the load from the flag buffer happens. What X is set to happens like above this address, so it would be set in a basic block that calls this location. And to get to those basic blocks, we need to kind of look backwards from this particular address or this address to what's calling that address. It might be possible to put together a Radare2 command that can kind of do that temporary seek and iteration, but I haven't figured out what the magic incantation is. And we don't really need to because we're sitting here in a Python environment. We can put together any kind of script we like. So first up, we know that these invalid instructions happen because of stateful disassembly. It turns out from trial and error that if you just disassemble the whole block, you will get the correct state. So let's just do that first, and we'll put the information into the little bit bucket there. Then we'll turn off the ASM lines so that we can do some grepping. We're going to do function disassembly of all the functions, looking for those 2 different ways that they could be referenced. And then we'll split the output by lines into an array. And then for each line, we're going to break it up and grab the first column. And then from that, we're going to seek to that location. And then we're going to do a disassembly print of 10 instructions. But we're going to do it from 6 instructions back from that location, or 6 bytes back from that location. And the 6 is a bit of a magic number that I found through trial and error. It's just the right size. If you were trying to do this yourself, you might start with like something like 24 or whatever felt right for your architecture, and then tune it to what would look good. Because the goal is really to be able to look backwards from this. And now you can see for each of these index loads, we can also see what value the X register is taking first. So there is a 0 offset copy of 5 bytes, that's flag dash. Then there's a something offset copy of 6 bytes at 1400, some value copy of 5 bytes near 1404, etc. So we know these are those cache register globals that we dealt with before. They're in 1400, 1404, 1408, and 140C. And what we need to do is just keep reversing backwards to see what the correct values are for those registers. So before we forget, why don't we mark them with some flags and mark up all the locations that reference those addresses with some comments, so we have some nice disassembly sugar for later. And then we'll go and disassemble. We'll disassemble all the functions and look at all the locations that are dealing with those pressed caches. Okay. And remember, in sequence 1, there was that initializer that put 0 in them in the init routines, no problem. Since we're hunting backwards, the offset values we looked up in the flag buffer, we want to know what is stored in those cache globals. So the STX instructions are actually the only part we're interested in. These are the parts where the particular value after test is going to be written into those locations. So we're going to do some more grepping. This time, because I haven't figured out how to chain greps, I'm just going to shell out to grep and then ask it to only show us those locations. Luckily, there's only 4. And what we can do is look at each of the basic blocks that are containing these STXs. And maybe we know that probably the basic block before it, where the tests are being performed on those joypad registers. So we put that together here too. We're using some more Python. You can recognize splitting by lines. We're grabbing out the first column. We're seeking to the location and then running this R2 command, which seeks to the start of the basic block and then disassembles the basic block by doing a temporary seek to AXT. We haven't covered this command yet. AX is the data references, which we talked about really briefly. T is all of the code to this location. So we're printing the basic block that precedes this basic block by seeking backwards to what jumps to it. and then we're printing the basic block we're in right now. So we're printing two basic blocks, the caller of and then the call target. And when we do that, we can see pretty quickly what values are supposed to be in those registers. So 1400 obviously has to have the value of X40 again, I believe. One of them doesn't work correctly. So this unknown 3 pressed cache, for some reason, doesn't work. What we're going to do instead is look at this at -6 bytes trick, which seems to disassemble pretty good. So we can use that one to read out what the correct value is for the 1408 register. So when we look at all that disassembly, and I won't make you, decode all of it, we can see that we need to have these particular values in those particular locations. And we know that those locations are in fact the offsets into the flag register. So we actually have all the information we need right now to print out the flag, because we know the lengths and the offsets. And for this challenge, because we went backwards, we don't even need to emulate it to put in the joypad inputs. We just can dump the flag from static analysis, which is pretty cool. Alrighty. Does anyone have any questions at this point? The only thing left is looking at a bug that's a non-bug. Take only a few minutes. Okay. So yeah, last application of the notebook. In trying to figure out why those invalid instructions are being spit out sometimes, it was handy to have this notebook view of Radare that let me kind of try some things, restart, do a lot of iteration, do a lot of experimenting. So let's figure out what went wrong. We open up that sequence 1, so we're looking at the sequence on target. You remember we're closing standard error. The disassembly at 8217 was the first time this showed up, and it was supposed to look like this with an AND of an immediate value of FF. But when we go there, we get this weird AND, and you can see it even grabs the number of bytes wrong. Right? So there's kind of a hint of what's going wrong here already before we even get to the end. But we know that by doing a disassembly of all the functions, stuff would just work. So we'll create a new R2 pipe session, and run a command in it where we just do basic analysis, and then we do analysis by following the call flow. This is a lot faster than the default analysis of AAA. And then we'll go ahead and do a disassembly of all the functions that are detected. And when we're done that, magically the disassembly works. So somewhere in disassembling one of these functions, some state changes that makes the disassembly correct. And one of the ways to figure that out is we could try each one at a time until the disassembly looks right. So let's store the expected value. Let's then also store all of the functions, because it's expensive to do the analysis. And then for each function, we're gonna create a new Radare instance, and we'll perform the basic analysis, AAC. We're gonna use a particular name when we start up here. We'll do one disassembly of just that function. And then here's the JSON output feature that we talked about. So printing a disassembly with JSON output of 3 instructions, and doing that with the command J function, means that it'll automatically take this output and turn it into a Python dictionary, so that we can access the array natively and then access the elements natively, just to get that disassembly. So we're doing the comparison as expected, and then if it matches, we'll print the hex offset. And then we have a quick break, because it turns out there's a lot of ones that'll match, but we don't need them all. We just need a couple candidates for our own analysis. So these are the candidate functions that are going to fall out. Find those, and then we know that that disassembling any one of those functions will actually do the thing we want. So for example, just disassembling that initialization function at 8000 will do the trick. So then we have to ask ourselves, what is it about them that makes that state change? Is it the last instruction? So we can actually disassemble at a particular location, and then look at just the output. But none of these functions share the same last couple of instructions. They have different last instructions. So maybe it's, the first function, first instruction, and they have different first instructions. So it must be one of the opcodes that's inside the function. And what we can do then is actually iterate over all of the possible opcodes and all the possible functions and find ourselves the one instruction in all of them that is going to do the trick of doing all the side effects to make the disassembly right. And this one actually takes quite a while. So here's another funny picture to help us pass the time. I always found this one pretty difficult. Why is bi-monthly mean both things? It's very frustrating. So there's one that came out, and it'll run a little bit longer. We will just interrupt it for the sake of brevity. So we can, the other one that comes out is 8362. What are these instructions? They are the SEP instructions. And if you know any disassembly of Super Nintendo, you already know why this is happening. But we figured it out by iterating over the whole binary. And we can actually set up a minimal test case. So at this point, I was still thinking it was a bug. It's not a bug. And we can even set up a test case that doesn't use the binary. So this is an example of opening standard in, setting the architecture, doing memory mapping for the writes, and then you can actually just write the hex bytes directly, even at a different location, then just do disassembly. So all of this one is a self-contained test case that has the contents of the memory in the Radare commands itself. Now, what's actually happening is totally expected behavior. That SEP instruction is responsible for setting status bits, and the particular bit that's being set there is it selects how wide memory accesses to the accumulator register are, which is exactly why any instruction changes the number of bytes that get decoded depending on the value of that flag. So it's totally expected behavior. All right, which brings us to the end of the workshop. I hope you learned something. I hope maybe this can be useful to you. I'm going to be using the same method to try to solve some more microcorruption challenges in the future. And I'm hoping to do a more detailed walkthrough of that SNES challenge at MonterHack in May, if that all comes together. So yeah, hope to see you all in the real world. And thanks for your attention.
Wow, that was incredible. I guess my first question for you would be, when did your world of Super Nintendo start?
Yeah, I think I got a Super Nintendo actually, you know what? It started because back in the day, do you remember video rental stores?
Yeah.
Yeah. So we had a video rental store in my hometown, Kirkland Lake, and it allowed you to rent video games. And I rented the Super Famicom with the Super Mario World cart, and that was my first Super Nintendo experience. And I was definitely hooked right from that moment.
But that name you used, I thought that was the name for. Was that the name that was used here? I thought that was only the name used in Japan.
Right, and I distinctly remember that the rental I had the rainbow-colored D-pad, not the purple ones. So, yeah.
How did they get that particular version?
I mean, I'll never know.
That's incredible. So this has really been a long-term relationship you've had, and and it obviously shows. I guess what was the impetus for bringing in Jupyter? I'm not sure how many people are familiar with Jupyter. I know I'm sort of a Jupyter noob, but perhaps that's your preferred development environment.
No, I think a lot of the stuff I've done in the past is more just command line based. I love living in the console, but I know that it's been a bit of an impediment to communicate some of my. It's not a great communication tool to like give somebody a markdown file, even though it's where I really like to use. And putting together a Jupyter notebook that is captures the embedded graphics and the formatting, as well as being self-contained so someone can rerun it, has been pretty powerful for kind of storing ideas that I need to come back to when I might not remember what the heck I was thinking about, or for downloading that information for other people. And then that was really useful for micro-corruption, going through those levels, using Anger and exploring it. But then being able to leverage Radare. I mean, I hope this was a decent learning tool. As a presentation, it might not have worked super swell, but I bet you going through the Python notebook offline could be really helpful, because there's a lot of detail in the, particularly in the write-up for the Super Nintendo Challenge on that gist. And I think it's a good way to download info.
Well, and as well, seeing as this is recorded, then people can follow along as well when they've missed a point or something like that. So,
yeah.
So that's going to be, useful as a presentation mechanism. I find it fine. The other question I had was the challenge that you worked through. How long were you working on that till you got that flag?
Oh, so at NSEC, I think we were one of the first solves. I mean, it didn't take us too long, but like the thing that I showed wasn't necessarily the path we took. The CTF solves are way more haphazard. Like we're just trying stuff, and you don't have the benefit of like that hindsight or that 30,000 foot view. You don't really know what's going on. So we did a lot of dumb stuff. Like I spent a bunch of time patching the binary, and then we only had that one working laptop with SNES, so I patched the binary and then sneaker net it over to the laptop and run it and see what would happen. And then we discovered that there was definitely data entanglement in the binary, and then we had to go back and start figuring out, okay, well, if there's data entanglement, we need to know what the correct button pushes are. And then I wasn't as confident with some of the Radare commands, so in the end, we made macros for SNES and like put them in as frame perfect commands for the first solve. The second one, because we had kind of leveled up on the Radare2 commands, the second one is really close to how we solved it. We went backwards from flag, and we were able to work out what were the locations storing those registers. That one we kind of flew through on sequence 2 because we had already kind of done all the tooling. But sequence 1 was just trying stuff, throwing it at the wall, and just failing.
Right. So, what's the next con you're involved in?
I definitely won't miss NORSEC. That's I love that conference for sure. May is pretty busy. I think I'm going to be doing some training for the Ottawa ISAC, which is going to be great with Dream Team LLC. Maybe Cyberboat. I'm not sure if that's happening. And of course, my main client, the NMFTA, is having their cybersecurity workshop in May as well. So May is chock-a-block. It's going to be fun.
Is that all in meat space?
Yeah, strangely, still all meat space. It's going to take some getting used to. But I'm looking forward to it.
Well, if you share with me the links, I'll put it on our Twitter feed and all our usual our Slack as well, so I can share that as well.
Thank you.
Yeah. So thank you very much for this. This has been an education. I feel like I need to do a lot of reading up. So you've given me my first step into a larger world.
Excellent. That'd be awesome.
Awesome. So with that, we'll just look. Are there any other questions? No, there are no other questions. So we'll sign off until next month, where we'll hopefully still be here and I'll have a new bingo card. So thanks again. And we'll catch you next month.
All right. Take care. Thanks again.
Thank you.